All right, let's begin our series of 3 separate lessons on approximation theorems in continued fractions, beginning with the convergence of continued fractions, for which we'll derive the strongest theorems. So let's remember some notation. If x is any real number, we defined x naught to be x, then a sub n was an integer part of xn, cn was the remainder or fractional part, and provided that wasn't 0, you define the next x sub n plus 1 as 1 over that remainder cn. So the integers Pn and Qn are defined recursively. They begin with initial terms. P naught is A naught, Q naught is 1. P1 is A naught A1 plus 1, and Q1 is A1. And then from that point forward, both P and Q follow the same recursive pattern, where Pi or Qi respectively are given by the partial quotient Ai times the previous term in the sequence plus the term before that. Then the limit, as n tended to infinity, of the Pn over Qn will be x, provided that the a sub i's were the partial quotients generated by x. Now, when x was rational, the process terminated and the sequence Pn over Qn will simply stop at a certain point at the value of x. When x was irrational, however, it went on forever, and we did prove that the Pn over Qn do converge to x. In fact, more precisely, in the event of an irrational x, we established that the even index terms are increasing with limit x and the odd index terms are decreasing with limit x, from which it definitely follows that x has to live in between 2 consecutive terms of the sequence. Note from the string of inequalities above that x is definitely in between p0 over q0 and p1 over q1, but it's also in between p1 over q1 and p2 over q2, and it's in between p2 over q2 and p3 over q3, etc., etc. We also showed, by the way, that for any index n, pn plus 1 times qn minus pn times qn plus 1 is negative 1 to the n. Okay, so the first thing we're going to show is that the convergents Pn over Qn are quite close to x. Specifically, x minus Pn over Qn is strictly smaller than 1 over the product of 2 consecutive denominators. And what's notable here is that it's not just the denominator you started with Qn, which is what's involved in the approximation on the left, but multiplied by Qn plus 1, which is the next denominator which is not being used in the approximation on the left. So x is in between Pn over Qn and Pn plus 1 over Qn plus 1. So if x is in between those two terms, well, the distance from x to one of them is definitely smaller than the distance in between both of them. And simply by giving them a common denominator, we see that the distance from x to Pn over Qn is strictly smaller than the quantity Pn plus 1 times Qn minus Pn times Qn plus 1 over Qn times Qn plus 1. But we've already established that that numerator is a power of minus 1, so in absolute value it's definitely 1. So the distance from x to Pn over Qn is less than 1 over the product of 2 consecutive denominators, the one you used in your approximation, Pn over Qn, and the next one, Qn plus 1. And continuing, we'll show that if x is an irrational number, which generates the partial quotients a sub I, you can also represent it as the following limit: the original integer part a naught plus this alternating sum. Notice you have negative 1 to a power on the top, an alternating sum of 1 over the product of 2 consecutive denominators. So let's just denote x sub n to be a partial sum here, a naught plus the sum running from index 1 to n. Now, if n is equal to 0, the sum on the right has no terms in it, and you just get a naught, which is indeed equal to p naught over q naught. So let's inductively assume that xn is equal to pn over qn. Well, then if I wanted to compute pn plus 1 over qn plus 1, I could start with that, add and subtract pn over qn. However, over here, we've already established that pn plus 1 over qn plus 1 minus pn over qn is simply negative 1 to the n over qn times qn plus 1, and we also inductively assumed that pn over qn could be replaced with x. But now note that we have x sub n is this sum, and then what are we adding to it? Exactly the next term we would have here. So we end up with xn plus 1. So what we've inductively proved is that pn over qn is simply equal to these partial sums, and the limit of the pn over qn we already know is the irrational number x. So x can also be written as this alternating series. Third step, for all n, the distance from x to pn plus 1 over qn plus 1 is strictly smaller than the distance from x to pn over qn. What this is saying is that we know the sequence of convergence, pn over qn, is converging to x. However, every term is closer to x than the one before it. So we've expressed x as this alternating series right here. And it's an elementary property of such series that the partial sums converge to their limit in a strictly monotone way. Essentially, You are adding and subtracting alternatingly due to this power of -1, bits that are getting strictly smaller. Okay, way in the past we established that the q's are strictly increasing. So starting from a initial value of a0, you are adding and subtracting smaller and smaller pieces. So those are getting closer and closer to the eventual limit x. We also showed in a previous proof, by the way, that those partial sums are exactly Pn over Qn, meaning the Pn over Qn are converging to x in a very strict way. So they are converging to x, each term being closer to the last, which is exactly the claim of this theorem. So now we can look at what are best approximations. So suppose x is an irrational number. The rational number p over q, we're not necessarily saying it's a convergent or anything like that, just a rational number. We call it a best approximation of the first kind if x minus p over q is strictly smaller than x minus a over b for any choice of rational number a over b where b is less than or equal to q and you didn't actually have exactly the same thing. In other words, of all the rational numbers whose denominator is up to and including q, p over q is the closest one to x. That is a best approximation of the first kind. If you strengthen this a little bit by multiplying both sides by their respective denominators, if qx minus p is strictly smaller than bx minus a for the same choice, you call it a best approximation of the second kind. This is not quite measuring rational numbers being close to x, but measuring multiples of x being close to integers. So on the left here, we have this multiple of x is closer to the integer p than this multiple of x is to the integer a. It's a subtle difference, but they are different things. They're related, as I mentioned, if you multiply this side by the denominator q and this side by the denominator b, then you end up with this expression right here. Note, however, that q is bigger than or equal to b, so you're multiplying this side by something bigger and this side by something smaller. So there's not a direct correspondence. You can't just get from one of them to the other. So they are different notions. Now, while they are different notions, they are related. Suppose you have a best approximation of the second kind, then it is also a best approximation of the first kind. We say that, therefore, the second kind best approximation is a stronger approximation. If you are best of the second kind, you are automatically best of the first kind. So let's assume that p over q is not a best approximation of the first kind. In other words, there is a rational number a over b whose denominator is less than or equal to q, which is closer to x than is p over q. If we multiply the two inequalities, specifically we have b is less than or equal to q, and this is less than that, so we're going to multiply them together. We get bx minus a is less than qx minus p, meaning that p over q is not a best approximation of the second kind. So if you're not a best approximation of the first kind, then you are not a best approximation of the second kind. The contrapositive is the statement of the theorem. The converse of this theorem, by the way, is not true. Okay, so if you are a best approximation of the second kind, then you are a best approximation of the first, but not necessarily in the other direction. So we'll get more into that later, but it's not going to be the focus of this video. This is now going to turn our attention to best approximations of the second kind. We'll look at first kind later. Okay. This puts us in a position to state and prove sort of the grand introductory theorem regarding strength of approximations in continued fractions, which is, suppose x is a positive irrational number. If p over q is a best approximation of the second kind, then p over q must be one of the convergents of x, except possibly if n equals 1 and a1 equals 1, and conversely, with the exception of n equals 1 and a1 equals 1, all of the convergents pn over qn are also best approximations of the second kind. So with this odd little asterisk on maybe a1 is equal to 1 and you're looking at p1 over qn, and we'll see why that exception pops up. Other than that, best approximations of the second kind are exactly the same thing as convergence of continued fractions. So as a proof, why are we assuming x is positive? Well, best approximations of the second kind all happen within absolute values. So if x was negative, you would simply reverse p and q, and it wouldn't really matter at the end of the day, but it's going to simplify our computations. So first, suppose that you have some choice of p over q, which is not a best approximation of the second kind, meaning it's possible to find a and b where b is less than or equal to q, so that bx minus a is less than qx minus p, meaning the multiple bx is closer to the integer a than the multiple qx is to the integer p. So what we'll do is we'll show that P over Q cannot be a convergent. That will establish the second claim. If not best approximation of second kind, then not convergent. We'll establish if convergent, then best approximation of the second kind. So let's assume to the contrary, that our choice of P and Q, which is not a best approximation of the second kind, is actually one of the convergents, Pn over Qn. Now the trick of this proof, due originally to Lagrange, is to represent the integers a and b as linear combinations of the numerators and denominators, Pn's and Qn's, of the convergence in a very particular way. Specifically, we set up this system of equations right here, that Pn alpha plus Pn plus 1 beta will be equal to A, Okay, so far what we've done, we're working to prove the second part of this theorem, that if you are a convergent Pn over Qn, then you are a best approximation of the second kind. So we assumed we start with a convergent Pn and Qn, and that we are not a best approximation of the second kind. Okay, so there is a choice of A and B, so that Bx is closer to A than Qx is to P. And what we did is we found unique integers alpha and beta, so that A can be represented as alpha Pn plus beta Pn plus 1, whereas B can be represented as alpha Qn plus beta Qn plus 1. We're trying to get a contradiction here. That will finish the proof that if you are a convergent, you do have to be a best approximation of the second kind. So notice we have B is less than or equal to Qn. Since B is less than or equal to Qn, you cannot have alpha equal to 0. Otherwise, B would be a multiple of Qn plus 1, which is bigger than Qn. Okay, so alpha cannot be 0. But if beta were equal to 0, then the only choice of alpha, for which alpha Qn equals B doesn't contradict the fact that B is less than or equal to Qn, would be alpha equals 1. But if alpha equals 1 and beta equals 0, that simply gives us that A is equal to Pn and B is equal to Qn, but our assumption was that Bx minus A was strictly smaller than Qx minus P. So that violates the assumption, because remember that P was Pn and Q was Qn, so we can't just have them be equal. Okay, so alpha can't be 0 and beta can't be 0. But again, since B is less than or equal to Qn, alpha and beta have to have opposite sign. If alpha and beta were both positive, this would simply be too big. And if alpha and beta were both negative, I'd have a large negative number here, and B is not allowed to be negative. So alpha and beta can't both be positive, and they can't both be negative. So let's look at that absolute value, Bx minus A. We go ahead and substitute in that B is alpha Qn plus beta Qn plus 1, and A is alpha Pn plus beta Pn plus 1. We distribute and collect terms to factor an alpha out of what we can and a beta out of what we can. Now the terms Qnx minus Pn and Qn plus 1x minus Pn plus 1 also have opposite sign. If you just imagine this parenthetical term and divide by Qn, you'd have x minus Pn over Qn, and here you'd have x minus Pn plus 1 over Qn plus 1. But remember, the convergence Pn over Qn alternate being larger than x and smaller than x. So I'm not claiming which of these is positive or negative, but one of them is positive and one of them is negative. So one of alpha and beta is positive and the other is negative. One of these is positive and one of these is negative. So either you have positive positive and negative negative, or negative negative positive positive, or negative positive positive negative, or positive negative negative positive. Either way, this term here, alpha times this parenthetical term, and beta times this parenthetical term are either both positive or they are both negative. So when you take the absolute value of the sum, it splits apart exactly equal. Either this was positive and this was negative, in which case this absolute value is not necessary, but neither was this one. They're simply equal. Or this was negative and this was negative, in which case when you add them you have a negative, but this will still be equal to the sum of these two absolute values here. Okay. And now all we do is we ignore this second term right here. Okay, so this sum is strictly bigger than this one, and we factored the alpha out of it. So what we've done is we've contradicted our assumption that the distance from Bx to A is closer than from Qx to P. Because what do we have? We have the distance from Bx to A is bigger than in the absolute value of an integer of the distance from Qx to P. So since this is the absolute value of an integer, remember alpha and beta were integers, this is at least as big as 1. So we ended up showing that this is actually bigger than that right there. And remember, we assumed that Qn was equal to Q and Pn was equal to P. So we contradicted our assumption that we were not a best approximation of the second kind. So this proves that if you are a convergent, then you are a best approximation of the second kind. Okay, so we're halfway through this theorem. We've proved that the convergents P over Qn are best approximations of the second kind. Now we need to prove the other direction, that best approximations of the second kind are convergents, with the possible exception of when you have a P over Q whose denominator is 1. So let's assume that P over Q is not a convergent to X. What we need to do is show either it's not a best approximation of the second kind, or the denominator has to be 1. So let's assume the denominator isn't 1 and show that it is not a best approximation of the second kind. Now the Qn's are strictly increasing with the possible exception of A1 equals 1, in which case Q0 is defined to be 1 and Q1 is defined to be A1, which is 1. So a while back we proved that the denominators Qn are strictly increasing except possibly Q0 equals Q1 when A1 equals 1. This is the source for the exclusion in this theorem. Other than that, if Q is not equal to 1, there is a unique index n for which the denominator Qn is less than or equal to Q is strictly less than Qn plus 1. Then we consider the same system of linear equations from before, so alpha and beta are integers that solve these two linear equations. Now since Q is less than Qn plus 1, but bigger than or equal to Qn, we still conclude that alpha and beta can't both be positive, because then Q would be too big, and can't both be negative, because then this would end up being a negative number. So we can do the same arguments about opposite sign to substitute in P and Q for these linear expressions here. Because these can't both be positive and can't both be negative, and these are of opposite sign, the absolute value splits apart just like it did in the previous half. And this is strictly larger than throwing out this absolute value entirely, factoring out the integer alpha and pretending it's the smallest possible value of 1, and you end up with that distance is bigger than Qnx minus Pn. So what we did is we found a choice of integers, Qn and Pn specifically, so that this multiple of x is closer to this integer, closer, less than this multiple of x was to this integer. So what we found is that P over Q is not a best approximation of the second kind. So starting off with P over Q not being a convergent, it is not a best approximation of the second kind. That completes the proof. Other than the possible exception of Q equals 1, convergence and best approximations of the second kind are exactly the same thing. So having proved that theorem, let's put it into action with a couple examples. Suppose x is the square root of 2, whose continued fraction expansion begins with a 1, and then after that is all 2's. Find the multiple of root 2 closest to an integer out of the first 1,000. So out of root 2, 2 root 2, 3 root 2, 4 root 2, and so forth, all the way up to 1,000 times the square root of 2, which one of them is closest to an integer? Well, rather than list them all out with a calculator, what we know now is that best approximations of the second kind exactly tell us integer multiples of the number closest to integers. So we're looking for a best approximation of the second kind, P over Q, whose Q is as large as possible, because if you go further down the list, you'll get better and better approximations. But we don't want to include anything larger than 1,000. So what we're looking for are convergents, specifically what Pn over Qn are the largest terms possible, meaning individually Pn and Qn, not the ratio. So which of them are the biggest possible until you pass the Q, the denominator, being 1,000. So we start computing P0 over Q0, A0 over 1, 1 over 1, P1 over Q1, A0 A1 plus 1 over A1. Remember, A0 is equal to 1, but all of the other ones are equal to 2. So the first terms in our approximation to root 2 are 1 and 1.5. Now, after this point, all of the partial quotients are 2, so all we have to do is take 2 times 1 numerator plus the one before it. 2 times 3 plus 1 is 7. 2 times 2 plus 1 is 5. 2 times 7 plus 3 is 17. 2 times 5 plus 2 is 12. 2 times 17 plus 7 is 41. 2 times 12 plus 5 is 29, and so forth and so forth. We keep computing P over Q, and we get 99 over 70, 239 over 169, 577 over 408, 1393 over 985. Now definitely if I compute the next term, I'm going to get a Q larger than 1,000, so we're going to stop here. So what was the last in the sequence of Pn over Qn whose denominator was not bigger than 1,000? 1393 over 985. What that tells us is that out of all the rational numbers whose denominator is up to and including 985, the one whose integer multiple of root 2 is closest to an integer is 985 root 2 is very close to 1393. And you're not going to get any closer until P9 over Q9, but Q9 is definitely going to be larger than 1,000, and we were given that as a cutoff. So out of the first 1,000 multiples of root 2, 985 root 2 is the closest to an integer out of all of them. So let's wrap this up with another example. Given that e has the rather interesting continued fraction expansion, which is true, but we won't derive, its integer part is 2, then we have this pattern 1, 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, 1, 1, 10, 1, 1, 12, 1, and so forth. Which positive integer up to and including 1,000 is closest to an integer multiple of e? So this is kind of a reverse of the previous problem. We're not asking which multiple of our irrational number is closest to an integer, but rather which integer is closest to a multiple of our irrational number. So we want the last numerator Pn up to and including 1,000. So we start computing our convergence Pn over Qn. We end up with a0 over 1 is 2 over 1. That's not the worst approximation for e, but a little better is P1 over Q1, which is a0 a1 plus 1 over a1, or 3 over 1. 3 is indeed a bit closer to e than 2 is. We just keep computing our Pn over Qn. Just be careful, a1 is 1, then a2 is 2, a3 is 1, a4 is 1, a5 is 4, a6 is 1, and so forth. If you keep computing convergence, you'll get 8 over 3, 11 over 4, 19 over 7, 87 over 32, 106 over 39, 193 over 71, and then 1,264 over 465. So the positive integer up to and including 1,000 that's closest to a multiple of e is actually 193, which is awfully close to 71 times e. This might be a little surprising. If you keep listing out multiples of e, 72e, 73e, 74e, 75e, none of them ever get closer to an integer than 71e was to 193 until 465e is very close to 1,264. But every multiple of e from 72e up to 464e will be further away from an integer than 71e was to 193.